Hello friends. Today's lecture we're going to continue with pile capacity. I'll briefly summarize the total ultimate load carrying capacity, as you know, is summation of end bearing and shaft bearing. End bearing is similar to spread foundation, and Terzaghi bearing capacity equation can be applied with a little bit modification. Modification should be done for n factors. Sometimes when diameter is relatively small, we can neglect this component and we can continue with these two components. And well, what about frictional resistance? Frictional resistance is dependent on frictional resistance between soil pile interface. So we need unit frictional resistance, and we will calculate later, multiplied by site area. Then, as usual, we have to consider a safety factor. 2.524 is enough. Now let us estimate these frictional resistance, unit frictional resistance, and QP and bearing by means of in situ test results. As you know, we use SPT and CPT test results generally. Of course, we have more than 2 tests, but these two are very common in all over the world, as well as Turkey. When we use SPT test results, as you remember, SPT test results should be modified, should be corrected for energy ratio. This 60 means SPT number corrected for 60% energy ratio. Then our equation for QP and bearing includes N60. PA we use generally, this is atmospheric pressure, and in terms of kilopascal, we can use hundreds, and then multiply with L over D ratio. L length and D is diameter. And we have a limiting value. The calculated value should be less than and equal this limiting value for PA and 60. When we use CPT test results, we can assume QP and bearing capacity is equal to QC. What was QC? QC compensation resistance.
Hocam ikinci vize için ne söylediniz? Bir daha tekrar edebilir misiniz?
Neyi ne söyledim?
İkinci vize olacak mı? Bir daha söyleyebilir misiniz?
İstiyorsanız yaparız. Son hafta yaparız.
Hocam hiçbir şekilde istemiyoruz ya. Zaten finallerimiz, derslerimiz çok ağır. İkinci bir vizeye gerek yok artık. Zaten peki, sınavlar da az. Yani ben öyle düşünüyorum. Arkadaşlarım çoğu da böyle düşünüyor.
Aranızda karar verin. O sizin menfaatinize bir şey.
Yani tamam hocam, itiraz eden olursa da zaten o zaman mail atarız ki hangi mailler daha çok sonra göre karar verirsiniz.
Şu birinci sınavı bir açıklayayım da biraz da ona göre karar verirsiniz.
Aynen
az kaldı.
Hocam.
Bitireyim, açıklayayım.
Tamamdır. Çok teşekkür ederim hocam.
Devam ediyorum. For sandy soils, you know, sands and clays behave different. If our soil is sand or sand-dominated soil, sandy soil, the pond bearing capacity, QP, generally increases with depth. As you see here in blue line, but at a definite depth, it becomes a constant value. This is critical depth, L over B or D. After this depth, QP is constant and equals to QL, limiting value. This limiting value can be calculated by this equation, 0.5 PA NQ star and tangent of internal friction angle. This NQ star is modified bearing capacity factor, and this is dependent on internal friction angle and can be taken from this plot. In x-axis, you see internal friction angle, and crossing this blue line, you can determine NQ star. This is limiting value, and QP, which is calculated by using this equation, should be less than limiting value. This is important for clays. For clays, N bearing capacity is equal to N modified NC, undrained shear strength, and area. This is just modification of Terzaghi equation, because as you know, internal friction angle, let me show here, internal friction angle and internal friction angle dependent, these two terms will cancel, only first component remain. So bearing capacity and bearing capacity for clay soil is very simple, NC, Cu, and area. This NC factor for zero internal friction angle soil, for clay soil, can be taken as 9. So final equation is 9 Cu A. What about frictional resistance? Frictional resistance or site resistance in sand is calculated for every layer, and total capacity is summation of frictional resistance for every layer. Here we need a side area. Side area can be calculated delta L multiplied by perimeter. This is area of sides for one single layer, of course, multiplied by F, unit friction. The magnitude of critical depth, of course, similar to before case, unit friction increases in sand down to a critical depth, and after this critical depth it will be constant. The magnitude of this L prime critical depth for medium compact sand and compact sand is around 15, and 15 to 20 pile diameters. For z equal to 0 to L prime, I mean this portion, that's 0 to L prime, unit friction can be calculated by using passive earth pressure methodology. Here K is effective earth pressure coefficient and sigma prime effective vertical stress. Then we need an interface friction angle, soil pile friction angle, in other words. And this F should be less than F critical. As you remember from soil mechanics course, this K varies with depth and approximately equal to Rankine passive earth pressure coefficient Kp. So we can use Kp at the top of pile and maybe less than the at rest pressure coefficient K0 at a greater depth. Based on presently available result, the following average values of K can be used. For bored piles, 1 minus sine phi prime. Low displacement piles, for example, H section piles, K0, 1 minus sine phi prime to 1.4 K prime. For high displacement piles, concrete piles or closed-end pipe piles, this is 1 minus sine phi to 1.8 K0. And interface friction angle vary in the range from 0.5 phi to 0.8 phi. Unit friction can also be determined by using in situ test results. Again, we will use SPT and CPT test results. The average unit friction resistance for high displacement driven piles may be obtained from average SPT resistance. Please note that corrected for 60% energy and 60 multiplied with atmospheric pressure, you can take it as 100 and 0.02. This is for high displacements, driven concrete piles or closed-end piles. For low displacement piles, open-ended pipe piles or H-section piles, this coefficient this constant value 0.02 reduces to 0.01. Anyway, depending on pile type, the frictional capacity of a pile will be multiplication of P times L. What is this? This is side area. Side area multiplied by unit friction. Qs can be estimated using the frictional resistance obtained during cone penetration test, frictional resistance. In this method, F can be obtained just multiplying FC, CPT test results, multiplied by alpha prime, a constant, and alpha prime comes from this plot. depending on pile material type, timber, steel, concrete. As you know, timber is rare today. Steel and concrete piles are used generally. And you can take alpha prime, multiplying with FC, unit friction, and thus QS can be determined. Frictional resistance in clay is somewhat complicated, and we use 3 different methods depending on drainage conditions and field conditions. Alpha, beta, gamma. Alpha, beta, gamma methods. Let us start with lambda. Alpha, beta, gamma, not alpha, beta, and lambda method. Let us start with lambda method. This method is based on assumption that the displacement of soil caused by pile driving results in a passive lateral pressure at any depth, and that the average unit skin friction will be dependent on effective stress, plus, of course, CU, undrained shear strength, multiplied with lambda. Lambda is also dependent on pile length, and we can use this plot, this curve, and for definite pile length we can use this table. These two are the same. This is effective stress, but sigma prime, sigma 0 prime bar. This bar means effective vertical stress for the entire embedment length. So, putting into the equation this calculated F average, QS can be determined. And one important thing here, how can we determine this sigma bar and CU? These two are mean values, but weighted average should be used. For calculation of mean CU, we will sum up CU multiplied by length of the soil layer, CU multiplied by length of soil layer, and we will divide cumulative of these terms to total length, weighted average for layer thickness. This is average internal average cohesion. For mean effective stress, sigma bar, we will use this methodology. First of all, we will draw a vertical effective stress curve according to the depth. Remember from soil mechanics course. For every layer, effective stress will be changed linearly. Why? Because this vertical effective stress is equal to unit weight multiplied by length. Unit weight is constant, only changing thing is depth. So in one layer, it is very linearly. After plotting this diagram, we will calculate area for every layer And sigma bar is equal to summation of all these areas divided by total length. These two are important for this simple equation. In alpha method, the unit skin resistance can be represented by this simple equation. We will multiply undrained shear strength with alpha value. Actually, alpha is dependent on Cu value, and Cu corrected with atmospheric pressure gives a better results. So we will use Cu over Pa values. Pa is atmospheric pressure. And we will take alpha value from this relationship and put here. So our final QS equation, epsilon alpha Cu multiplied by side area, P delta L. And beta method. When piles are driven into saturated clays, the pore water pressure in the soil around the piles increases. How much? Up to 4 to 6 times of Cu. However, this pressure, this increase in pore pressure, dissipates gradually. Hence, the unit frictional resistance for the pile can be determined on the basis of the effective stress parameters of clay in a remolded state. Remolded, in other words, drained condition. In drained condition, instead of undrained state, in undrained state, remember, internal friction angle is 0 and cohesion becomes undrained shear strength, a constant value. However, in drained condition, cohesion will be equal to approximately 0 and internal friction angle is a number, not 0. In beta method, unit friction is equal to beta multiplied by effective vertical stress at any depth, and beta equals to K, earth pressure coefficient, multiplied by tangent of drained internal friction angle. And again, remember lateral earth pressure from soil mechanics. K can be calculated using this equation for normal consolidated clays. If our clay is rather aged clay, old clay, having some amount of OCR or consolidation ratio, we will multiply this equation with square root of OCR. But as you know, all consolidated clays are rare. And combining these equations, finally, for normally and over-consolidated clays, unit frictions can be calculated using these long equations, and total side friction, whatever the method is used, and F comes from the method, multiplied by side area, P times delta L. Let us make a summary of these three methods and try to understand which method should be used in which conditions. The alpha method is a conventional total stress analysis for the skin resistance of piles in cohesive soils. The skin resistance is related to the average soil undrained shear strength using one single coefficient alpha, adhesion factor. The beta method is an effective stress analysis which considers the frictional resistance for the soil shaft interface. In this method, the side resistance is a function of horizontal effective stress and effective stress friction angle for the soil shaft interface. The lambda method is a combination of total and effective stress analysis that can be used for cohesive soils. In this method, the side resistance is related to undrained shear strength and effective stress as well. Sometimes our piles will settle on a rock. So we need to calculate point bearing capacity of piles resting on rock. And point bearing capacity of rock basement can be calculated using this equation here. In this equation, Qu is unconfined compressive strength, or in other words, uniaxial compressive strength of rock, and this is bearing capacity factor for rock and calculated using this relationship. Phi prime is internal friction of rock, not soil, above. But we have to consider a scale factor in determination of Qu, unconfined compressive strength, because rocks are generally heterogeneous and mass behavior of rock mass is rather different than a small core sample. Scale factor is considered using this relationship. Qu value, which is determined in the laboratory, will be divided by 5 to get a design value, considering the scale effect. As usual, we will apply a safety factor. Safety factor can be taken as 3. So, allowable bearing capacity is calculated using design value, unconfined compressive strength value, multiplied by n factor and divided by factor of safety. This Qu comes from laboratory tests, but to get rough information, you can use these two tables, Qu and internal friction angle, depending on different rock types. For example, for sandstone, it varies between 70 to 140. For example, for granite, this is the hardest rock. It ranges between 140 to 210. Sometimes it may be more than 250. Anyway, let us solve an example question about pile foundations. This example question is from your textbook. Example 9.1. Pile length is 20 meters. Pile type is concrete. And geometry cross-section is square. 0.407 meter diameter. And soil type is sand. Unit weight of sand and also internal friction of sand. These two parameters are given. We will calculate ultimate point capacity using Meyerhof methods. In Meyerhof methods, we have a limiting value, and calculated value is main equation will be increased according to depth, but should be less than and equal to limiting value. Take an internal friction angle 45 from table 9.5. You will determine NQ vector as 143 and multiplying unit weight 18 by length, surcharge value can be calculated as 360. What else? We have determined M factor, surcharge Q prime. That's all for main equation. So the main equation gives you 8,528. It's rather high, extremely high value. Let us check limiting value. Just calculating using this equation. Actually, multiplying with 0.5 and tangent phi. We know all parameters, just put here. And the limiting value is 829. Let me show the plot. Not this plot, but similar. The capacity increase with depth. Sorry, yes, this equation. Increase with the depth. But after critical depth, it stays constant. So we have to use this value as design value. QP will be equal to 829. Example 9.2. Consider a pipe pile, but closed end, with closed end, flat driving point. So it's high displacement pile. The diameter of pile is 457 millimeter, and the length is 20 meter. We have 3 different layers, and unit weight and Andre shear strength values are given for every layer. The groundwater table is located at 3 meters from the surface. And Meyerhoff's simple equation for clay type soil is this 9CuAp, which unrange shear strength value will be used to 5, 40, and 90. Because end bearing is only related with the soil around the end of the pile. What was the length? This is 20, and 20 meters comes here at this layer, 10 to 30. So we will use this value, 90 value. Just putting 90 here and geometrical things anyway. QP is 132.9. Example 9.3. We have concrete pile, square pile. Dimensions are given. Length is 12 meters. In this table, N60 values are given. SPT results corrected for 60% energy. In this example, we will estimate QP, end bearing capacity. For end bearing capacity, when we use SPT results, the average of these SPT values should be used. But average of which results? It's actually 10D above and 5D below the pile tip. Where is pile tip? Pile tip is at 12 meters. 5D, this is around 1.5. So our average starts with from this value. What about the upper level? 10D. 10D is around 3 meters, and 10D, 10 diameter, is around here, and these 4 value should be used in calculation of average value for QP. But when we calculate side resistance, we will use all SPT values down to end of the pile. I mean this blue rectangle. For QP, we will use this orange rectangle. 5D below, 10D above. This relationship, let me show, yes, from this failure zone is shown here 4D, but sometimes it's taken as 5D, because failure zone extends to pile shaft around 10 diameter. Let's come back to example. Yes, average of these 4 values is 16.5 and approximately 17. Just put here in this equation PA can be taken as 100 and average and 60. 17. We know L and D. And the result is approximately 633. And this can be used as design value. In the next question, next example, we will consider this pile in example 9.3 again. But in this question, we will calculate allowable load carrying capacity of pile. So we need side friction. And for side friction calculation, again, we need average SPT value, but in this case, we will use all SPT results measured along the side of the pipe. And average N60 in this case will be approximately 10. What was our equation? F average equation for high displacement pile, concrete pile, and driven pile. So we have to use equation for high displacement, and this constant value is 0.02. Putting all things here, QS can be calculated as 292.8 because we just calculated QP in the example 9.3. We can take the value from here. QP plus QS end bearing and side bearing. This is total ultimate capacity. Multiplied, divided by safety factor. We can use 3. Now this is allowable capacity of pile. 308.6. We have one more example. Again, 12-meter concrete pile. Having 450 millimeter diameter, and the cross section is square. Soil type is clay, and water table is located at 5 meters. And soil parameters, both unit weight and underhand shear strength change at 5 meters depth. Above the groundwater level, underhand shear strength is 50 kilopascal, and below the groundwater table, underhand shear strength is 75 kilopascal. Similarly, unit weight values are also different. Is 17.4 above groundwater table and 18.1 below groundwater table. We will determine pile capacity using lambda method. Lambda method is rather simple, but in lambda method we need effective stress value average effective stress value and average undrained shear strength value. Using the methodology given in your book, let us start with average undrained shear strength. Undrained shear strength multiplied by layer thickness, 50 times 5. Let us do for another layer, 75 multiplied by 7, divided by total length. During calculation of average effective stress, first of all, we have to draw effective stress change diagram, and we will consider these areas. First area from 0 to 5 meters, because this is triangle, 87 multiplied by 5 thickness divided by 2. This is multiplied by 0.5 is the same. For second layer, the mean of 87 and 145 multiplied by layer thickness 7. After calculating average values, just putting into the equation, F average is 51.6. So multiplying with side area, total shaft resistance is 1114 kilonewton. One more example, similar example. This example was not from textbook, but this is from textbook, example 9.7. Referring to this figure, what we see here, actually we have two clay layers. But first clay layer is divided by groundwater table, and above and below groundwater table soil parameters are changing, both internal, cohesion, undrained shear strength, and gamma unit weight values are different. We will use again beta method. Beta method phi r is given, and the clay is normally consolidated. First clay, the top 10 meters is normally consolidated. The bottom clay is over consolidated with OCR2. We will multiply with square root of OCR. And we will calculate the skin resistance. By beta method and alpha and lambda method as well, using 3 methods. And in section B, using the results of example 9.2, estimate the allowable pile capacity using safety factor 4. Let us start with part A. And we need to calculate, we need to determine alpha value, which is dependent on the CU. Again, we need to determine CU from from this soil profile, and we will multiply with side area. And alpha can be taken from 9.10 table. CU values were given. Just putting into this equation, layer by layer, these are calculated, and summation cumulative of all these values are 1050 kilonewton. In second, this is alpha method. In the second part, we will use lambda method. The equation is given here, but we need average effective pressure, and again average Andre shear strength. Andre shear strength is calculated, average Andre shear strength, layer thickness multiplied by Cu divided by total length. All things are given in this table. 25 multiplied by 3, 40 multiplied by 7, and 90 multiplied by 10, divided by total length 20. This is average Andre shear strength. To calculate sigma bar, average effective stress, we need to draw this diagram, and we will use area for every layer. The summation of areas divided by total length is sigma bar, and 98.85 kilopascal. Of course, we need lambda from the table 9.9. Alpha, lambda is 0.173. And what else we need? Nothing. Just putting previously calculated parameters. F average is 38.81. Multiplied with side area will give you 1114.4 kilonewton side resistance, shaft resistance. In part 3, we will use beta methods, and we need to consider internal friction angle, but remolded or drained value. It was given as 30 degrees. Again, we need average value, average sigma for different layers, considering over consolidation ratio. Of course, first two layers are normally consolidated clay, but the bottom layer is over consolidated clay, so we need to multiply with square root of OCR for OCR2. This is the F average for layer 3. Just summation of these three F value multiplied by side area will be equal to 158.45. Part B is ultimate bearing capacity. So we just calculated QS, but we need QP. QP can be taken from the previous example as 151, and just putting into equation from the alpha, lambda and beta methods. These three values are almost equal, and the result is 306 kilonewton. Do you have any question for these example questions? You can ask. If you don't have, I want to go into pile load test. Pile load test is similar to plate load test. We use a hydraulic jack and 3 dial gauges, and of course 2 reference beams. It's very similar. Generally we use neighboring piles as anchor pile, or sometimes we use dead loads above the reaction beam, but it's rare. Generally, neighboring piles are adequate. Step loads are applied to the pile, and sufficient time is allowed to elapse after each load so that the small amount of settlement occurs. This is the reason why we apply loads step by step. The settlement of the pile is measured by dial gauges. Each step load is about 1/4 of the proposed working load. The load test should be carried out to at least a total load of 2 times the proposed working load. After the desired pile load is reached, the pile is gradually unloaded. As shown is unloading curve here in this equation. For any load on this blue curve, the net pile settlement can be calculated just subtracting this elastic settlement, because as you see here, the y-axis is settlement and loading results in settlement. But when we unload, some amount of settlement is recovered. So this portion is elastic settlement. But this amount is plastic deformation or stationary settlement. So for any load, to calculate net pile settlement, we will subtract elastic settlement SE from ST. For example, for Q1, ST1 minus SE1, for Q2, ST2 minus SE2. These are net settlements. And to determine ultimate bearing capacity, we can use both the maximum value or the maximum curvature or linear steep linear portion start. These two values can be used depending on the behavior of curve. Pile foundations show elastic settlement. An elastic settlement of a pile is the result of elastic settlement of pile material, SE1, because pile material, concrete is also elastic material. Settlement of pile caused by the load at the tip of the pile tip, soil around pile tip is also elastic material. In other words, may show elastic displacement, and SE comes from the elastic behavior of soil under the pile tip, and settlement of pile caused by the load transmitted along pile shaft. This is SE3. And final settlement of our pile will be summation of these three. If the pile material is assumed to be elastic, of course we can assume, the deformation of the pile shaft can be evaluated using this relationship which comes from elasticity theory. Here, QWP is load carried at the pile point under working load condition. QWS, load carried by frictional or skin resistance. EP, modulus of elasticity. AP, area of cross section of pile, and length, of course, length of pile. You see a coefficient here, and this value varies between 0.5 and 0.67, and will depend on the nature of the distribution of the unit friction resistance F along pile. You can take it as 0.5. The settlement of a pile caused by the load carried at the pile point may be expressed in this equation, which is similar to initial settlement or immediate settlement of spread foundation with some modifications. You are familiar with ES modulus of elasticity of soil around pile tip. This diameter again, QWP, load per unit area at the pile point, and what else? Poisson ratio, you are familiar, and influence factors similar to spread foundation, and you can take it as 0.75. The settlement of a pile caused by the load carried by the pile shaft can be calculated using this equation. We use perimeter and length. This is side area. You know QWS And ES, soil elasticity, is are the same. Influence factor here, IWS, and IWS influence factor is dependent on pile geometry, and you can calculate IWS using this equation: pile diameter, pile length divided by pile diameter, and summation of these three is equal to settlement of pile, total settlement, in other words. Do you have any question up to now? If you don't have any question, I'm gonna stop, and next week we're gonna continue with negative skin friction and group piles. After solving some questions, we will end the pile foundations next week. I'm stopping now if you don't have any question. I think you don't have any question, and see you next week.